Okay, let's look at a very fundamental concept in statistics, and that is the normal distribution, also referred to as Gaussian distribution or bell curve. Bell curve for the obvious reason that the curve just looks like a bell, and Gaussian distribution after the German mathematician Carl Friedrich Gauss, who also invented the Gauss algorithm, but that is not directly connected to this one here. The name normal distribution does not come from the normal everyday use of normal in terms of common, but from the mathematical sense, because the mirror axis of this curve is in a right angle to the x-axis, like this. So the curve is symmetrical. That's why it is called normal distribution. However, if this name makes you believe that the bell curve is extremely common, you're still right. It shows in countless fields and statistics. For example, when you measure the height, the weights, or the IQ scores of humans, but also when you look at, for example, errors and tolerances in production processes, or even when you roll a number of dices and you document your average number of eyes, you will always find a normal distribution. And especially the last example shows that this is not a psychological or biological phenomenon, but rather a mathematical phenomenon. So let's look at 3 different examples. And I would like to start with the probably most common and most boring, but still very useful one of human height, or the height of adult humans. Let's say the average adult human is something about 1.70 meters. I don't know exactly, but let's just assume 1.70 meters. Then this will be here in the center of our graph. But there are also people who are, for example, 2.10 meters and taller, or there are people who are 1.30 and smaller. But these are very rare exceptions. Most people will be very close around 1.70. Let's say between 1.60 and 1.80 will be the big mass of the people, but there will still be many people around 1.50 to 1.90. But it becomes less and less. The majority of the people are somewhere here around the middle. So here we see a bell curve. And in this case, 170 would be our mean value. The mean value is nothing else than the average. So you get the mean value when you add all your values together and then divide them by the number of values. And the mean value is always a vertical line in the middle. So that would be 170 in our case. For another example, when you order a new car, there will be a slight variance in power that it makes. Many people are not aware of that, but let's say the average of this car model with this engine and so on is 200 horsepower. Then there will be cars that have 205 horsepower or maybe only 195 horsepower. There might even be cars that have over, let's say, 220 horsepower or below 180, but that is very rare. Why is that? Because this depends on many factors. For example, the tolerances of the parts that the manufacturer uses for the engine. And you have so many factors that they would all have to align in the same direction for either positively or negatively to result in an extreme result. For example, all the parts would have to be exactly in the middle of the tolerance, exactly in the sweet spot to bring the engine to 220 horsepower. Or they would have to all really push the limits of the tolerance to make an engine that only makes 180 horsepower. And that all these factors align in the same direction is very unusual. So you would most likely always have cars around this 200 horsepower because the positive and negative impacts of the various factors will always more or less balance each other out. Or let's say you would be rolling dices. You have 6 sides, so you have a mean per die of 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by the 6 sides. So you would have an average of 3.5. So that would be also your mean. Let's say you have 10 cubes or 10 dice. You would have a mean of 3.5, and you could theoretically have an average of 6 or an average of 1, but that is really rare, because for that you would have to roll only 6s or only 1s. In the most cases you will have something around 3.5, let's say between 3 and 4, depending on how many dice you roll. And that already brings me to my next point. Even when you have a normal distribution, there are differences. For example, you could have a curve, I hope I managed to draw it freehandedly now. You could have a curve that looks like this. Well, this should not be completely vertical, but you get the point, that it's more narrow and a little bit more pointy than this curve. Or you could have one that is wider, like this. And how can you have that? Well, for example, with the size of the adult humans, you might already look at a smaller predefined group. For example, instead of looking at the world population, you could look at male Swedes, for example. So you would have less variance in your values, and they all would be much closer to the mean value. Or if you roll the dice, you might just use more dice. If you only use 4 or 5 dice, you might have a result like this, because only 1 6 too many would have a huge impact on the average. But if you roll 1,000 dice, then you will get very close to this average of 3.5. This phenomenon is described with the standard deviation. The standard deviation describes how much your values differ from the mean value, and therefore it describes how wide or narrow your graph is. Now, the standard deviation is not exactly the width of the graph. The formula for that is a little bit more complex, but when you have a normal distribution, you can say that approximately the middle 2/3 are one standard deviation. So it is directly related, but it is not 1-to-1. What defines a graph is basically the mean is the center of the graph, the mirror axis, and then the standard deviation defines the width of the graph, and the height of the graph depends on your y-axis and how you present your values and what values you have. One more thing I want to mention is that you might run into a situation where somebody is talking of a normal distribution, but you see a curve like this in an S shape. And that can actually be, for example, when every value also includes the value to the left, so the smaller value. For example, if you don't describe the exact size of adult humans, but when you want to describe how many adult humans are below a certain size, for example, you say they are below 2.10 m, because then, of course, you would have the highest slope here around 170, but because all people that are below 170 are also below 210, but there are still people, even more people below 2.10 m, the graph would still increase. So it will go up all the time, but it will flatten out to the area where the values go down. So yeah, that just as a little comment on the side, so you don't get confused if somebody is talking of a normal distribution and then you don't see this bell curve but an S-shaped curve. Let's investigate the curve in more detail to get an understanding of why we observe this behavior. We could already clarify why the highest density of results is around the mean in this area. But let's recap one important point. In regards to the cars, I said that many factors would have to align into the same direction in order to lead to an extreme result that is somewhere in this area. It is more likely that they balance each other out and land here, right? But why is that the case? Assuming that the probability of each factor to have a positive or negative impact is the same, a specific result would like where all factors balance each other out is just as likely as a scenario where all factors align into one direction. Let's make that clear with a table. Let's assume we have a table and each column is one factor in the car production. So for example, we have the piston size. If they are exactly in the sweet spot, or too big or too small, and if you want the crankshaft bearings, and so on and so on. There are countless factors. So this is our table. And let's imagine it was binary. Of course, in reality it isn't, but the system is the same, and it's easier to clarify it this way. So let's say a 0 is for we are really pushing the limits of the production tolerance, and a 1 is for we are exactly in the sweet spot, and we just ignore everything in between. Okay, then a distribution like 1, 1, 0, 1, 0, 0, where all factors balance each other out, is just as likely as 1, 1, 1, 1, 1, 1, right? So why is it more likely that we land in the middle where they balance each other out? Well, that is simply for the reason that this here is equivalent to, for example, 0, 0, 1, 0, 1, 1. It's a different pattern, but we still have factors that even each other or that balance each other out. The more factors we have, the more possible combinations we have that lead to the same result, but they do not increase linearly like this, but they increase exponentially. The more factors we have, the more different combinations there are that lead to the same result, and they increase exponentially. While in order to get an extreme result, like all positive factors, there's always only one way. It doesn't matter if you have 2 factors or 6 or 12 or 100, there always is only one way to fulfill all of them, and that is 1, 1, 1, 1, 1, 1 for the number of factors you have. So as you see, in scenarios where each single combination of factors, like these ones, has the same probability, because it is completely random, that's only the case when it is completely random, the deciding factor is the number of combinations that lead to the same result. And that explains why 1 and 6 are far less likely averages when rolling a number of dice, and 3.5 is the most likely one, because there's, no matter how many dice you have, there's only one way that leads to an average of 1 and only one way that leads to an average of 6. Of course, you can roll a 2 and you can still get very, very, very close. But if you want a clean average of 1 or 6, there's only one combination of cubes that allows this. Whereas for 3.5, there is a huge number of combinations that all lead to this result. So therefore, we basically explained the behavior in these 3 areas here. But why do we observe the behavior in between here? Why is the difference of probability lower between, let's say, 3.5 and 3.7 than it is between 4.5 and 4.7? And the difference of probability here is the slope of the graph, right? Why is it so flat here and in these 2 areas around the tails and at the peak? And why is it so steep in between? Because if you say, okay, the numbers of possibilities decrease to the extremes, we could still have a graph that looks like this, right? And we would intuitively say that this looks wrong and can't be, but it is much harder to actually explain why that is the case. To investigate that in more detail, I would like to divide this graph into 4 areas, and that is here from the left tail going right to the middle of this way, then from the peak to the left to the middle, from the peak to the right, and from the right tail to the left. So these 4 areas. But I'm only gonna really explain 2 of these areas, this one and this one, because as it is a symmetrical graph, what applies here also applies here, just in negative, but the logic is the same. Just like when you look at a negative picture and all the colors are in complementary, but you still recognize what you see on the picture, right? So what happens in this area? As we already established earlier, talking about the factors in car production, the number of possible combinations increases exponentially when the count of numbers increases, or the count of factors. So here, if we aim for an average of 2 and we roll a higher number than a 2, we only have the 1 to balance higher numbers out. But when we aim for an average of 2.25, we already have 1 and 2 to balance higher numbers out, which gives us exponentially more possible combinations that lead to the same result. And while the probability continues to rise up to 3.5, it continues slower after 2.25. We have an inflection point here, so the direction of the slope is changing. Basically, if you would have the derivative of this graph, this would be a local maximum. We have the highest slope around here, and then even though we continue rising, the slope decreases. But we have explained this area, right? We have more possibilities to get to the desired result, and they increase exponentially with the numbers that we add as possibilities to balance our results out. And this also applies here then. Now let's look at this area. What happens here? Like, why does it not increase even more all the time? And then we have basically like a pointy graph. Actually, here we have a very similar scenario as before, but now as we aim for bigger average numbers, the amount of numbers that can balance out to the low numbers decreases. So if we aim for an average of 3, we can balance lower numbers out with 4, 5, and 6. But when we aim for an average of 4, we can only balance lower numbers out with 5 and 6, right? So the number of combinations that lead to the same outcome decrease exponentially in this area. But as soon as we hit the next inflection point again of 4.75, the logic from here applies and basically overweights. So we have these two factors that work against each other, and in these areas at the inflection points, basically one becomes stronger than the other one, if we want to see it that way. So, and you can apply this one in negative to this side and the other way around. And this way we can explain for all 4 areas why that occurs, and that explains the whole bell-shaped curve. As you might see now, even though visually there's only one mirror axis in this bell curve, which is at the mean, from a logical perspective, this curve does actually have 2 mirror axes. And there would be a second one here. That's a little bit abstract, but I hope you can follow me. Because the same principle or the same logic that applies here for the exponential growth applies here, why it grows exponentially slower and then decreases. So basically it is as if you had an image that you do not only turn like this, but also flip it in that direction. So yeah, again, of course, this is not an optical mirror axis, but I would consider it a logical mirror axis. Sue me if I'm wrong, but for me that helps understanding it. Now, in the end, I would like to draw one more thing, which is nothing new after this video, but I hope that it sticks a little bit better with this visualization. Now, imagine we stick with the dice roll example, and you have 3.5 here, and you have 6 here. And you have, for example, the combination, let's say you roll only 6 dice to make it easier. You have the combination 1, 2, 3, 4, 5, 6 that leads to 3.5. But you also have 2, 3, 4, 5, 6, 1 that leads here. You even have 2, 2, 2, 4, 5, 6 that leads here. And you have countless more options that all lead to your average of 3.5. But you only have, now I'm going to hell, but anyway, you only have 6, 6, 6, 6, 6, 6. That leads to an average of 6. No matter how many cubes you have, the line just gets longer, but you need only 6s to get to an average of 6. Now imagine you have a blindfolded monkey throwing darts in this direction. What is he more likely to hit? Of course, he's most likely to hit one of these countless combinations that all lead to 3.5, and it is very, very unlikely that he hits here the only one combination that leads to the 6. Yeah, I hope that made it clear. I hope the normal distribution is now really understandable and this was a relatable explanation. And if there are any questions open, please let me know.